This man had lived with headaches for as long as he could remember. Not sudden, not explosive, just a constant dull pressure that came and went often enough to be annoying, but never severe enough to feel dangerous. For years he ignored it, until one day the headaches lingered longer than usual, joined by a brief weakness on one side of his body. Nothing dramatic, nothing that screamed emergency. Still, it was enough for him to finally do what he had been postponing: go to the hospital. He walked in on his own, no panic, no urgency, just another patient expecting reassurance. The examination was routine, the questions were standard. To be safe, the doctors ordered imaging, the kind done every day for symptoms like his. Even then, no one expected surprises. This was supposed to be confirmation, not revelation. Then the scans appeared. Inside the imaging room, the atmosphere changed instantly. A silence fell that had nothing to do with professionalism and everything to do with disbelief. The doctor stared at the screen, leaned closer, adjusted the contrast, then checked the settings again. At first, it seemed like a technical error. Machines fail, images glitch, but the picture remained the same. Nearly half of the man's skull was filled not with brain tissue, but with clear fluid. Where complex folds of cortex should have been, regions tied to speech, memory, awareness, there was nothing. No blood, no tumor, no surgical scars, no signs of recent injury, just absence. After several long seconds, the doctor finally spoke, quietly, almost instinctively. "Where is the rest of the brain?" What made the moment unbearable was what followed. The man in the next room was awake, calm, and fully aware. He spoke clearly. He understood everything. He answered questions without hesitation. He stood, walked, reacted. By all observable measures, he was functioning like any other person. CT scans, MRI scans, repeat imaging, different machines, different specialists. The conclusion did not change. A large portion of the cerebral hemisphere was missing, truly missing. Medicine is built on structure. Damage here causes loss there. Remove tissue, and function disappears with it. Yet this man was sitting upright, thinking, speaking, existing, while violating one of neuroscience's most basic assumptions. The question that echoed through the room was no longer about diagnosis. It was something far deeper. How does a human being live, think, and function when half of what we believe makes them who they are is gone? The first reaction was denial. Not emotional denial, but clinical denial, the kind medicine relies on to protect itself from impossible conclusions. When an image contradicts everything you know, you assume the image is wrong. That was the safest explanation. A mistake was far more acceptable than rewriting the rules of the brain. So the process started again. The scans were repeated, carefully, slowly, with different settings and different machines. The technicians recalibrated the equipment. The doctors reviewed the protocols step by step, searching for anything that could explain a false result. Artifacts happen. Software fails. Human eyes misread shadows. All of that was possible, likely even. But every new image told the same story. They brought in older scans, if any existed, and compared angles, depths, contrast levels. Nothing changed. The empty space was always there, occupying the same region, the same volume, the same impossible absence. Specialists were called in, radiologists, neurologists, neurosurgeons. Each one examined the data independently, without being told what the others had concluded, hoping fresh eyes might see what everyone else had missed. No one did. They considered psychological explanations next. Could this be a functional disorder? A dissociative condition? Something where symptoms exist without structural damage? But the images were not subjective. They were brutally physical. This was not perception or belief. This was anatomy. There were no surgical scars on the skull, no records of trauma, no signs of hemorrhage, infection, or recent destruction. The edges of the remaining brain tissue were smooth, not torn or inflamed, suggesting this was not a sudden loss. Whatever had happened, it had not happened violently. It had happened quietly, slowly. The possibility of tampering was dismissed. The idea of falsified images or manipulation collapsed under scrutiny. Too many independent systems, too many checks, too many professionals seeing the same thing. There was nothing left to blame but reality itself. At some point, the room reached an uncomfortable stillness, the moment when medicine exhausts its excuses, when repetition no longer brings reassurance, only confirmation. The scans were correct, the machines were functioning, the interpretations were consistent. The conclusion was unavoidable. A large portion of the man's brain was not hidden, it was not damaged, it was not inactive, it was gone. And yet the man remained. That was the moment the question shifted from what went wrong to something far more unsettling. If the brain tissue disappeared long ago and life simply continued, then what had been doing the work all this time? Once the shock settled, the investigation moved backward in time. If half of the brain was missing, the most important question was not how he was functioning now, but when the loss had begun. The answer mattered because a sudden injury should have left chaos behind: paralysis, loss of speech, collapse. None of that had happened. His life had unfolded quietly, almost normally. That alone suggested something far more disturbing and far more subtle. Doctors began reconstructing his neurological history like detectives piecing together a crime that left no obvious scene. One possibility stood out immediately: chronic hydrocephalus beginning in childhood. In this condition, cerebrospinal fluid accumulates slowly inside the skull, increasing pressure millimeter by millimeter, year by year. Not enough to trigger emergency symptoms, not enough to cause collapse, but enough to compress brain tissue relentlessly. Under constant pressure, neurons don't explode or bleed. They thin, they retreat. Over time, entire regions can be reduced to a fragile layer, and eventually, function disappears not with a scream, but with silence. Another possibility was even more deceptive: a slow, silent stroke. Not the dramatic kind that sends someone to the floor, but a gradual disruption of blood flow, subtle enough to avoid alarms. No sharp moment of failure, no clear line between the before and after. Just cumulative damage, spreading quietly, allowing the brain time to adapt as it loses ground. There was also the chance that nothing had ever disappeared at all. A congenital malformation could explain everything. The missing half may never have fully developed in the first place. From birth, the brain may have been incomplete, but functional. If that were true, the man had never known another version of himself. His brain would have grown, learned, and organized itself around absence, treating limitation as baseline rather than loss. What mattered most was not which explanation was correct, but what they all had in common. None of them involved a sudden event. There was no single moment when half the brain vanished, no instant of catastrophe, no dramatic failure that demanded immediate compensation. The damage, whatever its origin, unfolded slowly, over years, possibly decades. And that slow timeline changed everything, because the brain had time. Time to adapt, time to reroute, time to test alternatives and reinforce what worked. Instead of facing a cliff, it faced a slope. Instead of collapse, it faced gradual pressure. And in that space, the brain did what it has evolved to do when survival is threatened, but not immediately destroyed. It reorganized itself without asking for permission. The loss was real, but it was never sudden enough to overwhelm the system. Function didn't disappear overnight, it migrated. Responsibility shifted from one region to another, silently, continuously, until the absence became invisible to everyone, including the man himself. This was not a story of recovery after damage, it was a story of adaptation during damage. And that distinction would soon become the key to understanding how a human being could stand, speak, and think while carrying an absence that should not have been survivable. The answer, the mechanism that turned an impossible scan into a living, speaking human being, lies in a property of the brain that sounds almost poetic but is brutally practical in nature: neuroplasticity. This is not a miracle, not a hidden superpower, and not a loophole in biology. It is a survival system written into the nervous system itself, refined over millions of years to keep organisms alive when ideal conditions disappear. Neuroplasticity is the brain's ability to reorganize its own structure while it is still operating. Neurons are not fixed wires locked into a permanent blueprint. They are living cells that strengthen, weaken, disconnect, and reconnect depending on demand. When a pathway becomes unreliable or begins to fail, the brain does not immediately surrender the function it carried. Instead, it searches for alternatives. Nearby regions are recruited. Distant networks are repurposed. Tasks that once belonged to a single specialized area are broken apart and distributed across multiple systems. In this process, nothing dramatic announces itself. There is no alarm that sounds, no moment where the brain pauses and acknowledges loss. The change happens quietly, incrementally, beneath awareness. A function begins to lean slightly away from its original home. Another region picks up part of the workload. Repetition reinforces the new route, and over time, the original pathway becomes less necessary. Eventually, it may vanish entirely without the function ever disappearing. This is why neuroplasticity is not magic. It does not restore destroyed tissue. It does not recreate neurons once they are gone. What it does is far more pragmatic. It reallocates responsibility. It treats the brain not as a collection of irreplaceable parts, but as a dynamic system where roles can be reassigned when survival demands it. When damage occurs slowly, as it did in this case, the brain has the luxury of adaptation. There is time to experiment, time to fail quietly and correct course, time to reinforce what works before the old structure collapses completely. By the time the physical tissue is gone, the function has already moved on, anchored elsewhere, operating under a different architecture. The brain does not respond to damage by declaring defeat. It responds with a question, not "this area is destroyed, so we are finished," but "who else can do this job now?" And if the answer exists, even imperfectly, the brain will build around it, reinforce it, and commit to it until it becomes the new normal. In this man's case, neuroplasticity was not a last-minute rescue. It was a long-term negotiation between loss and function, carried out silently over years. The brain did not wait for catastrophe. It adapted in advance. And by the time doctors finally saw the absence on a screen, the system had already solved the problem it was never supposed to survive. The success of neuroplasticity in this extraordinary case did not come from chance. It was forged by three interlocking factors, each crucial, each unforgiving in its absence. First, the pace of the loss. The damage did not occur overnight. There was no sudden collapse, no acute trauma demanding an immediate, desperate response. Instead, the process unfolded slowly, imperceptibly, giving the brain a rare gift: time. Time to detect the failing circuits, time to experiment with alternative routes, time to reassign responsibilities from one network to another without catastrophic failure. Every gradual inch of decay allowed neighboring regions, and even distant ones, to adjust their roles, to practice, to strengthen the pathways that would ultimately carry the tasks of thought, speech, and memory. Second, the age at which this adaptation occurred mattered enormously. The brain in early development is fundamentally different from the adult brain. It is malleable, highly exploratory, continuously wiring and rewiring itself as it learns the rhythms and patterns of the world. In a child or adolescent, regions that are not yet fully specialized retain the capacity to assume entirely new functions. In this patient, the critical windows of brain formation were still open, allowing regions that normally would never have carried certain cognitive or linguistic duties to step in, to absorb, and eventually to dominate. This flexibility is a fleeting opportunity. Once the brain solidifies into its adult architecture, such dramatic reassignment becomes far less reliable. Third, and perhaps most decisive, was the sheer passage of time. Neuroplasticity is not instantaneous. It is the product of relentless adaptation over years, a continuous negotiation between loss and compensation. Every day, every experience, every minor cognitive challenge became a reinforcement session, guiding the brain in how to reorganize itself most effectively. The slow erosion of tissue was, paradoxically, what allowed the preservation of function. By the time the damage was complete, the brain had already rehearsed the new arrangements countless times, making the transition seamless, almost invisible from the outside. The ultimate revelation is profound. The brain did not lose its capabilities, it redistributed them, reallocating roles, constructing backup networks, and establishing entirely new operational hierarchies. What appeared to be an absence, a void on imaging scans, was in reality a triumph of adaptation. The mind continued to function, not because it was unscathed, but because it had been rewritten, quietly, meticulously, by the brain itself. This is the terrifying and exhilarating truth about neuroplasticity. It is both fragile and unstoppable, contingent on conditions, yet supremely effective when those conditions align. The preservation of language in this patient challenges one of the most deeply held assumptions in neuroscience, that the left hemisphere is the exclusive seat of speech and comprehension. Classical models taught us that Broca's area, Wernicke's area, and the surrounding cortical regions form an immovable command center, a fixed circuitry responsible for every word we speak and every sentence we understand. Yet here, with nearly half of that supposed command center missing, language did not vanish. It adapted, it survived, and it thrived. The right hemisphere, often considered a supporting actor in communication, stepped forward to assume the responsibilities of the damaged left. Regions that would normally process intonation, prosody, and emotional content expanded their roles, incorporating vocabulary, grammar, and syntax. Neurons began forming new connections, establishing entirely alternative routes for signals that had once depended on the now absent left side hubs. Pathways that had previously been auxiliary became primary, and networks that had never carried linguistic function were recruited, strengthened, and integrated into a cohesive system capable of fluent speech. This process did not happen overnight. It required years of gradual adaptation, subtle reinforcement through everyday activities, social interaction, and learning. Each conversation, each thought, each attempt at communication became a small rehearsal in a grand, unseen retraining program orchestrated by the brain itself. In essence, language became mobile. It was no longer bound to a single location, but existed as a flexible, distributed network capable of migrating when necessary. The profound implication of this observation is that our understanding of brain function must evolve. Language is not a fixed button to be pressed, but a dynamic system, a resilient architecture that can be shifted, reassigned, and rebuilt. In this patient, the right hemisphere did not merely compensate, it innovated, creating new networks, refining old connections, and proving that even functions we consider rigidly localized are, in reality, astonishingly plastic. This discovery rewrites the way we think about speech, cognition, and the very nature of the mind, revealing a capacity for adaptation that borders on miraculous, yet is entirely rooted in the biological reality of the brain's own survival instincts. Documented cases like these push the boundaries of what we think is possible for the human brain and force us to reconsider the very definition of normal neural architecture. In instances of chronic hydrocephalus, the cerebral cortex can become astonishingly thin, in some extreme situations almost completely absent, leaving what appears to be a vast cavity where the brain tissue should reside. Yet, remarkably, many of these individuals retain near-normal intelligence, continue to develop language skills, and live lives that are functional and meaningful. The brain does not merely tolerate these deficits, it adapts, reallocating responsibilities, rewiring networks, and ensuring that essential cognitive functions persist despite the dramatic structural loss. Even more striking are the outcomes of surgical hemispherectomies performed on children to control intractable epilepsy. In these procedures, one cerebral hemisphere, sometimes half of the entire cortex, is removed entirely. Conventional wisdom would suggest that such a drastic intervention should leave the child severely impaired, unable to speak, reason, or move normally. Instead, what clinicians have observed is nothing short of extraordinary. Over time, the remaining hemisphere reorganizes itself, taking on roles previously managed by the excised tissue. Children relearn to walk, to communicate, to solve problems, and to interact socially, often achieving cognitive milestones comparable to their peers. The brain, faced with an immense challenge, demonstrates a capacity for functional redistribution that defies our expectations of rigid localization. The shocking truth revealed by these cases is that half a brain, or even far less, can be sufficient to sustain life, language, and intelligence. The cortex is not a static map of fixed functions. It is a dynamic, adaptive system capable of transforming itself to meet the demands placed upon it. These examples underscore the profound resilience of neural circuits and highlight the incredible potential for recovery and adaptation, especially when injury or anomaly occurs gradually or early in life. They force us to acknowledge that what we often consider essential structures may not be as indispensable as we once believed, and that the brain's survival mechanisms are more inventive and robust than we can fully comprehend. Not everyone is granted this extraordinary capacity for neural recovery, and the reasons lie deep within the constraints of biology and timing. Neuroplasticity, as remarkable as it can be, is not a universal guarantee. It is a potential that depends on several critical factors. Age stands as the most decisive variable. Children's brains are still developing, with networks in flux and synapses forming at a breathtaking pace, offering a flexibility that adult brains simply do not retain. The younger the brain, the more easily it can reroute functions, reassign tasks, and rebuild circuits that were lost or damaged. The speed and nature of the injury also play a decisive role. Gradual, slow-onset damage allows the brain time to adapt, to experiment with alternative pathways, to gradually shift functions to healthier regions. Sudden trauma, by contrast, overwhelms these adaptive mechanisms, leaving little time for the brain to reorganize before critical functions are compromised. Similarly, the location of the damage is crucial. Some regions have more redundancy, more overlapping networks, more potential backups. Others are bottlenecks, essential hubs where loss cannot easily be compensated. Equally important is stimulation and rehabilitation. The brain's plasticity is not automatic. It is nurtured through use, challenge, and practice. Physical therapy, speech therapy, cognitive exercises, and environmental engagement all coax the brain into remapping itself, pushing neurons to form new connections and strengthening alternative circuits that might otherwise remain dormant. Without these deliberate interventions, even a young, flexible brain may fail to realize its full potential for recovery. For adults, the limitations are stark. Synaptic formation slows, neural circuits are more rigidly defined, and compensatory mechanisms are far less robust. Recovery is possible, but slower, incomplete, and often requiring far more effort and support. The adult brain may regain function, yet rarely with the same ease or completeness observed in children, highlighting that while plasticity is a powerful force, it is neither uniform nor limitless. The miraculous recoveries we see are the exception, not the rule, a testament to timing, adaptability, and the remarkable yet fragile design of our neural architecture. Neuroplasticity, as powerful as it may seem, is not a panacea. It does not magically restore the brain to its original state, nor does it erase every functional deficit or guarantee a return to pre-injury abilities. It cannot undo the physical reality of lost tissue, severed connections, or areas that are irreparably damaged. The risks of severe cognitive, motor, or sensory impairment remain present, and the path to recovery is often long, uncertain, and painstaking. Yet within these limits lies the true marvel of the human brain, its capacity to mitigate damage, to salvage what would otherwise be lost, and to reorganize itself in ways that preserve life, functionality, and identity. By redistributing tasks to unaffected regions, forming new networks, and adapting remaining circuits to take over critical functions, the brain minimizes losses and maximizes survival. Every recovered word, every regained movement, every small cognitive adjustment represents a triumph of this subtle, relentless force. Plasticity does not promise perfection, but it buys time, restores possibilities, and offers a lifeline that, without it, would simply not exist. It is the silent architect of resilience, reshaping the mind quietly, persistently, and almost invisibly, allowing life to continue in forms that were once thought impossible. What this extraordinary case and the many others like it reveals about the human brain is profound and unsettling in equal measure. The notion that specific regions of the brain are rigidly tied to fixed functions, that there exists a universal blueprint governing thought, language, memory, and action, collapses under the weight of these real-world examples. Each brain is, in essence, a singular creation, molded by genetics, experience, environment, and adaptation. The pathways we assume are essential may be abandoned, rerouted, or replaced entirely, and the capacities we take for granted can emerge in unexpected places. Your brain does not operate according to some fixed template. It is a living, dynamic system, continuously reassessing, reallocating, and optimizing itself in response to what life, and sometimes injury, throws its way. It works not like anyone else's, but in its own remarkably self-directed manner, a silent testament to flexibility, ingenuity, and survival. The lesson is clear. No two minds are identical, and what seems impossible in one context may be routine in another. Your brain, with all its quirks and redundancies, functions as an autonomous, self-organizing universe, capable of compensating, adapting, and thriving in ways that defy expectation and redefine the boundaries of what it means to think, to speak, to live, and to endure. The philosophical angle here is as subtle as it is profound. If half a brain can sustain thought, language, emotion, and a fully functional life, then we are forced to confront questions about potential. What latent abilities lie dormant in each of us, untested, unchallenged, simply because circumstance never demanded their activation? How many neural paths, cognitive strategies, and adaptive circuits remain untapped, quietly waiting for necessity to call them into action? It is both humbling and unsettling to realize that much of what we consider essential, rigid, or irreplaceable may in fact be far more flexible than we imagine. Layered onto this is the ethical dimension that cannot be ignored. Medicine stands at a crossroads between intervention and respect for natural variability. Could we ever justify removing parts of a brain prophylactically under the assumption that it might one day be redundant or less efficient? How should rehabilitation strategies evolve, knowing that the brain can reorganize itself in ways we still barely understand? Should fear of losing a specific area override our willingness to experiment with therapies that might save or even enhance life? Each question tugs at fundamental principles of identity, consent, and the very definition of personhood. And yet, for all the intrigue, for all the awe at what a half-brain can accomplish, there are no definitive answers, only open-ended, uncomfortable reflections that challenge not only medicine, but philosophy, ethics, and our understanding of what it means to be human. The story is a reminder that science often leads to more questions than it answers, and that the brain, in all its astonishing adaptability, remains a frontier that tests the limits of imagination, courage, and moral reasoning. The scientific warning here is crucial and cannot be overstated. These extraordinary cases, where half a brain can sustain cognition, language, and a seemingly normal life, are statistical anomalies, exceptions that defy expectation rather than rules to follow. They offer insight, yes, but they do not provide a blueprint for safe experimentation. Brain injuries, strokes, congenital malformations, these are not to be taken lightly. In the vast majority of cases, damage is catastrophic, irreversible, and life-altering. The margin for error is non-existent. Even minor trauma can cascade into profound deficits, and the delicate balance of neural networks can be shattered in an instant. Yet, within this extreme caution lies a deeper lesson about resilience, adaptability, and the untapped potential of the human mind. This story is not an invitation to risk, nor a prescription to challenge natural boundaries recklessly. It is a window into what the brain can achieve when given time, opportunity, and the remarkable capacity for self-reorganization. It is a testament to evolution's subtle genius, a reminder that even when faced with near impossible odds, the mind and body find a way to compensate, to redistribute, to endure. And so we close this chapter not with reckless optimism, but with measured awe, a recognition that while the brain's flexibility is extraordinary, it is also fragile, a treasure of complexity that commands both respect and reverent study.